In the Unit 4, continuation concept of magnetic fields. In this analysis, we are going to learn about Lorentz force equation and its applications. We know that the electric field can cause a force which may be either due to the charge which is in stationary condition or in movement. But an H field is capable of producing the force only because of the moving charge. This is the basic difference between the electric field and the magnetic field. In Unit 1, we have seen that the force due to the electric charge is defined by Fe is equal to the product of charge and the electric field intensity E. So Q into E. So now we will see the analysis of force acting on a moving charge due to the magnetic field. It is just defined by, when you see the equation it will be more clear with. In this equation, I have the analysis of force due to the magnetic field, which is the product of the charge Q, the velocity V, and the cross product of magnetic flux density, which is F is directly proportional to the charge Q. F is also proportional to the product of the velocity and the magnetic flux density. F is also directly proportional to the sine of the angle which it makes with respect to V and B. But we can rewrite the equation of VB sin theta as V cross of B. We know that the cross product is sine representation. So VB sin theta is replaced by V cross B. So F is equal to Q of V cross of B. Now to find out the total force on a moving particle due to the combined effect of electric and magnetic field, I am applying the superposition theorem. So F becomes equal to Fe plus Fm. So F becomes equal to QE, which is due to the electric field, plus Q of V cross of B, which is due to the magnetic field. So Q of, take out Q, E plus of V cross of B. However, this equation is called as the Lorentz force equation, which can be used to determine the electron orbits in magnetron, proton path in cyclotron, and the charged particle motion in the combined electric and the magnetic fields. The continuation concept is the force on the differential current element. How to find out the force on the differential current element? We have defined force due to the Lorentz force equation, Q of E plus of V cross of B. Consider the two materials. Current which is passing inward, current which is passing outward. This is due to the positive charges, this is due to the negative charges. This difference we can see. Now I am going to identify the force on the differential current element. So the force on the charged particle in the magnetic field is written by the basic equation. We know that F is equal to Q of V cross of B. So differential force dF is equal to dQ of V cross of B. Already in the previous analysis I have written F is equal to Q of V cross of B. So dF becomes equal to dQ of V cross of B. Now as I told in the figure, we have the material using both positive and negative charge analysis. By definition of volume charge density, we know rho V is equal to Q by V. So I can rewrite the equation Q equal to rho V into V. This is one set of equation. From this, differential charge can be defined by rho V dV. Therefore, the differential force becomes equal to dQ of V cross of B is modified as, in the place of dQ I am replacing rho V dV of V cross of B. But by definition I know that the current density J is also defined by rho V into V, where V is the velocity and J the current density. From this equation I can write rho V is equal to J by V. Now take this equation of rho V, substitute in the force equation. So rho V becomes equal to, what is it defined by? It is defined by J by V. In dF I am substituting. So it becomes dF equal to, in the place of rho V I have substituted J by V, dV as such V cross of B. So dF is equal to, cancel out the velocity, equal to, because V cross of B is equal to VB sin theta n cap. This is a known condition, cross product. So cancel out the like terms. I am left out with J, B, sin theta, dV of n cap. Now again what could be the modification? The material is carrying a current of I with a surface of ds. So I can write J, we know the definition of J, the current density is equal to the ratio of current and area of cross section. Here the area of cross section is ds, so J is equal to I by ds. Volume element is a product of line and the surface element. So dV is equal to ds into dl. That's what I have written over here. So I am substituting J, dV, all values in this equation. So the value is IDL. So upon substitution of J equal to, and the analysis of condition of dV equal to, the final modified equation takes up the form of, I have identified J dV equal to IDL. So IDL B sin theta n cap. This is differential force. How can I rewrite this equation? IB sin theta you keep as such dl of n cap. If I need force, integrate both sides. So F becomes equal to IB sin theta integral dl over a length of 0 to L. So it is I L, integral dl is L, B sin theta of n cap. So I can rewrite this equation as the force due to the differential current element as I L cross of B. This is a repeated equation which we make use of in the differential current element analysis of the magnetic field analysis. Thank you.